Hi, and welcome to what's going to be a series of 4 clips based around nucleophilic addition elimination for A-level chemistry. And I'm going to start in this first clip by giving you a brief overview of the generic reaction mechanism that we would see. And the important parts to be aware of are that we will have a carbonyl attached to some sort of leaving group. Typically that would be a chlorine or chloride, and this will be attached to an R group, giving us something such as ethanoyl chloride or propanyl chloride, or even something slightly more complicated such as an acid anhydride, which we'll look at specific examples of in the subsequent clips. But the carbonyl is going to be reacted with a nucleophile, and in this generic overview what we're going to use is an oxygen with a lone pair of electrons attached to another R group. Again, this could be an acyl group, it could simply be a hydrogen, but it could also be an amine or a primary amine also, and they will give rise to different products, which again in subsequent clips to this we will go through. And in the first instance what happens is the lone pair of electrons acting as a nucleophile, i.e. is wanting to find an exposed or slightly more exposed nucleus, and is going to be able to locate this delta positive carbon on this carbonyl group here, and the lone pair of electrons will attack that carbon, forcing out one of the doubly bonded pairs of electrons on the oxygen, which creates an intermediate step, which is different to a lot of the mechanisms you've seen whereby they're just one step, whereas this one creates an intermediary step whereby the oxygen, which was the original carbonyl oxygen, is now opened up to be an O- with this extra lone pair of electrons. The X group, the leaving group, is still attached to the carbon, but now we have this attached oxygen which has nucleophilically attacked the carbon within the carbonyl, attached to what was, say, the alcohol that we started with as the nucleophile. This intermediate step would have a positive ion, a positive charge on the oxygen here, and an oxygen minus charge at the top. Technically this intermediate is a zwitterion, having both a positive and a negative charge within it, and so we get a second step of this mechanism whereby the lone pair collapses back down to recreate the double bond, and this time kicking out the leaving group. This is a better leaving group than the nucleophile that's just come into it, and this then allows the X in the second step to be eliminated from that molecule, creating an X minus ion, which would be kicked out. But also we have to allow a proton here to fall off and satisfy that positive charge by donating the pair of electrons in the bond between the oxygen and the hydrogen in the bottom there, and this then allows the H plus ion to be lost from that molecule, allowing the final molecule to be created whereby the X has been lost, and we now have this molecule created as the product, whereby we have now introduced an ester bond in this example here, whereby we have the carbonyl now attached to the R group it was originally attached to, so we started life as the acyl chloride or the acid anhydride, and we've now incorporated this additional R group over here, creating in this example an ester, but as we will look at it later examples, we can also create an amide if we had changed this oxygen to perhaps a nitrogen containing species. But importantly, what we've done is also created the H plus ion and also the X minus leaving group. So for example, if the X had been a chloride, chlorine from the acyl chloride, and we would have had the hydrogen kicked out, then we could have created HCl as an example here, HCl being a strong acid. If we had used the acid anhydride, we'd have created a weak acid, and those two byproducts, either being strong acids or weak acids, are what give rise to some industrial considerations, which again we will look at in subsequent clips, specifically with the acid anhydrides, which is useful in aspirin preparation. But hopefully this gives a generic overview for additional elimination mechanisms, and what we're going to do, as I say, in subsequent clips is go through the specifics of the named examples in the AQA spec, specifically looking at acid anhydrides versus acid chlorides in their relevant reactions with water, with alcohols, with amines, and subsequently primary amines as well. And then looking at, in the final clip of the 4, we'll look at their relevance to potential polymerization reactions as well. Thank you, and I'll see you in the next clip.